This video is meant to give some details on the Multi-Dataflow Composer Tool Baseline Core. MDC Baseline Core is responsible of dataflow to hardware composition. This feature is meant to release the designer from the burden of manually mapping different input specifications into the reconfigurable substrate. MDC leverages on the dataflow model of computation. Each dataflow actor is mapped on a different processing element. Datapath merging techniques are used to compose different input specifications. If two or more input dataflows share the same actor, then a reconfigurable substrate is derived by instantiating in hardware a single processing element. This latter can be accessed by the different paths of data using programmable switching elements. The baseline feature of MDC automates this approach. Its front end is able to combine a set of input dataflows into a multifunctional dataflow specification, keeping trace of the system configuration. The datapath merging problem can be formulated by adopting a graph model, where each graph G is represented by a set of vertices Vi, which are the computational operations, for example an addition, and a set of edges EI that are directed connections between vertices. Then, a labeling function is defined. It is in charge of identifying for each vertex, or rather for each computational operation, the physical processing element that can perform it on hardware. At last, in order to merge a graph G into the reconfigurable graph G, a mapping function is defined. A vertex V of G is mappable with a vertex U of the reconfigurable graph G, which vertices set is V, if they have the same label. In the same way, if an edge between Vi and Vi' is in the edge set EI of G, then an edge between the mapping of Vi and Vi' in G has to be in the set E. The datapath merging problem can be defined as find G such that the costs, in terms of number of vertices and edges, are minimum. The outcome of the merging process G shall include, for each kind of vertices of the input networks, that is, for each possible label, a number of vertices equal to the maximum number of that type of vertex in the input networks, considered one at the time. This guarantees that G has the minimum number of vertices V. An optimal solution, in turn, is defined as a feasible solution with the minimum number of edges. The datapath merging problem is known as an NP-complete problem, so that heuristic methods are usually adopted in order to find its solution. The solution to the datapath merging problem that is implemented by MDC at the moment is based on a heuristic method proposed by the same authors that defined the problem itself. The solution acts iteratively, combining two graphs at a time. At each iteration, given two input dataflow graphs and according to the related label functions, a compatibility graph is built. In this graph, each node represents a feasible edge mapping, that is a pair of edges, one for each dataflow, that can be mapped in the same physical connection on the reconfigurable graph. Each edge of the compatibility graph indicates that the connected nodes, feasible edge mappings, are compatible. Compatible, in this case, basically means that they can be implemented on the same reconfigurable graph. The maximum clique on the compatibility graph gives one optimal solution to the datapath merging problem. According to the maximum clique found within the compatibility graph, an optimal reconfigurable graph is derived. The back-end of the MDC baseline component generates the RTL description of the corresponding coarse-grained reconfigurable substrate and its configuration management logic. To do that, MDC requires two additional inputs from the user, a library of HDL components, which are the processing elements capable of realizing the functionality of the different actors of the input networks, and a description of the hardware communication protocol adopted by these components to exchange data. MDC standalone is not able to provide full design automation for coarse-grained reconfigurable systems. The HDL components library is not generated internally. However, MDC can be seamlessly integrated with tools, namely high-level synthesizers, capable of providing this missing feature. In theory, any kind of HDL components library can be adopted. It is only required to the user to properly describe the adopted communication protocol. By means of a simple XML file, the user can specify system signals of the components, for example clock and reset, predecessors and successors, like the FIFOs. And finally, communication signals, which represent the handshake protocol to be implemented among the actors. In order to provide full automation, MDC has been integrated with Turnus and Chronos, specifically conceived for the MPEG RVC Cal community. These tools perform respectively optimization in terms of FIFO dimensioning and high-level synthesis to provide the HDL components library. They leverage on dataflow graphs described with the RVC Cal formalism, which uses XDF, an XML dialect, for graph connections and Cal for actors. The target is limited to Xilinx FPGAs, since Chronos is target-dependent. To overcome this limit, we connected MDC also to CAF Studio. This latter is capable of performing optimization and HDL components library synthesis. FIFO dimensioning, for optimization purposes, is carried out by means of System C simulations. CAF Studio is platform agnostic, meaning that it can target any kind of hardware technology, FPGAs from any vendor, and ASICs. In the next few slides you will see how to set the parameters in the user interface to run MDC Baseline Core. Specify how many networks you intend to merge and add them to the XDF list of files as a comma-separated list. You can choose to generate the multi-dataflow specification only, or, as in this case, to generate the hardware substrate by adding the XML protocol file specification and the HDL component library. To learn more about MDC and its applications, here are some references. Please take a look to the next video to learn more about MDC additional features.